All right. Good evening, or I guess good morning if you're a procrastinator and you're eating breakfast while watching this video. But welcome to the first online lesson, and this will be covering section 2.5, which is about combinations of functions. So I guess let's just get started. So what is a function? And we've talked about this before. A function is a pairing or a relationship that assigns exactly one range value to each domain value. So domain and range, that would be our x and our y values. So out of all the x values that we're able to use for our function, it only assigns one y value to each one domain value. So another way you could look at this is if you use the vertical line test, but you would have to do that graphically. So if we drew our function, a vertical line would only intersect our function once, and at most once. So what we're going to be doing is we're going to be taking these functions and we're going to be adding them, we're going to be subtracting them, multiplying them, dividing them. So just performing different operations and seeing what happens when we do those things. Let's say that f and g are two functions that overlap. Their domains overlap, which means that they have x values in common. So then for the x values that they do have in common, we can add them, subtract them, multiply them, and divide them. So we can say that the sum of f and g is f plus g in parentheses, and then we're going to put an x in parentheses right behind it. And this is just notation, and what this really means is we are saying we are adding f of x plus g of x. So those are both going to be different values that we get once we plug x into our function. And we'll see this later when we do a couple different examples. So moving on to the difference. The difference between f and g would be f minus g in parentheses with an x in parentheses following it. And that means that is the same thing as writing f of x minus g of x. The product of two functions, so f times g, is the same thing as saying f times g in parentheses and then x in parentheses behind it, and that is equivalent to saying f of x times g of x. So I'm sure that you can start to see the pattern. And so for quotient or division, the last operation that we will be doing with functions, we can say that f divided by g of x is the same as saying f of x divided by g of x, so long as g of x is not 0, because if it's 0, then we're dividing by 0, and that is not good. If you remember Mr. Lee's poster up on the whiteboard, you don't want to divide by 0. You'll blow up your house. So I guess an easier way to see it is if we do some examples. So let's just jump right in and we'll do some examples. And these are in your notes. Given f of x is equal to x plus 5, and then g of x is equal to 3x, we need to find all of the following. So we're going to do the addition of both of those functions, the difference of both of those functions. We're going to find the product of them, the quotient, and then we're going to plug in some specific values that both of those functions take on, and we're going to find what y value happens. What y value do we get when we add or subtract or multiply or divide those functions together at that specific x value. F plus g of x. Well, that equals f of x plus g of x. If we look back to our equation, or to the notations that we wrote just right before this section. So we know that f of x is equal to x plus 5 and g of x is equal to 3x. So all we have to do is just add those two functions together. So we get x plus 5 plus 3x. So if we combine like terms, we get 4x plus 5. Let's move on to b, the difference between f and g. So f minus g of x equals f of x minus g of x, which is the same as saying x plus 5 minus 3x. And if we combine like terms for that, we get negative 2x plus 5. So for part C, that notation is the same as saying f of x times g of x. So what we're going to do is we're going to just take f of x and we're going to multiply it by g of x. We have the quantity x plus 5 times 3x. So what we need to do is we're going to distribute our 3x into the x and then over to the 5 as well. So when we do that, we get 3x times x, which is 3x squared, plus 15x. And that's what you get when you take f of x times g of x. And that's our answer. For part D, the quotient of f and g of x, that's the same as saying f of x divided by g of x. So all we need to do is substitute the different equations in for f and g. So we get x plus 5 over 3x. And we can sort of simplify this if we divide x by 3x and then we divide 5 by 3x. The x's cancel out in the first term, so we're left with 1/3 and then plus 5 over 3x. So for part E, we're plugging in an x value of 1. And so we're going to get a specific y value, the f plus g of 1. So this is the same as saying we're going to take f of 1 plus g of 1. So f of x is x plus 5. So 1 plus 5 is 6. G of 1 is 3x. So 3 times 1 is 3. So 6 plus 3 is 9. And that's going to be the answer. For part F, which is the difference of f and g at x equals 2, all we have to do is plug in 2 into f and then into our g functions. And so then we're going to subtract. So f of 2 is equal to 2 plus 5, which is 7. And then g of 2 is equal to 3 times 2, which is 6. So 7 minus 6 is 1. For g, which is the product of f and g at x equals 3. So all we have to do is plug in 3 in for f of x and then 3 in for g of x. So we get 3 plus 5, which is 8, and then we get 3 times 3, which is 9. So then 8 times 9 is 72. Another way you could look at this problem is back in part C, we found the product of f and g of x. And so all we have to do, or all we could do, is plug in 3 for x up in that equation, which is 3x squared plus 15x. So if we do that, we get 3 times 3 squared, which is 9, plus 15 times 3. So we have 3 times 9, which is 27, plus 45, which is 72. So we get the same answer either way. And the last one, f divided by g of 4. So plugging 4 into f, we get 4 plus 5, which is 9. And then plugging 4 into for g is 3 times 4, which is 12. So we have 9 divided by 12, which is the same as 3/4 once we reduce that fraction. So it's not too bad, eh? So if we flip over in our notes, which I know you all have and you're diligently filling out as the video progresses, we're going to do one more example. So let's say that f of x is 1 over x, and g of x is going to be equal to x divided by the quantity x plus 1. So we need to find the following. We need to find f plus g of x, we need to find the difference of the two functions, the product of the two functions, and then the quotient of those two functions. So for part A, f plus g of x, well, that's just equal to 1 over x plus x divided by the quantity x plus 1. So in order to add these two fractions, we need to have the same denominator. So we're going to multiply the left by x plus 1 over x plus 1, and then the right by x over x. And we get x plus 1 over x plus 1 times x plus x squared over x plus 1 times x. So if we add those two together, because they have the same denominator now, we get x plus 1 plus x squared over the denominator, which is x times x plus 1. And we can simplify this a little bit. If we group our first two terms in the numerator, we can divide that by x squared plus x, and that is 1. And then we're left over with 1 divided by x squared plus x, because you still have to divide the 1 in the numerator. So that is our answer, 1 plus 1 over the quantity x squared plus x. For B, which is the difference between f and g, all we have to do is subtract the two functions. Much like the question we just did, part A, we have to get the denominators the same, so we're going to multiply the first factor by x plus 1 over x plus 1, and we have to multiply the second term by x over x in order to get the same denominator, so we can subtract them this time, and that yields x plus 1 over the quantity x squared plus x minus x squared over the quantity x squared plus x. So now we can combine both of these fractions, we can subtract them, and we get negative x squared plus x plus 1 over the quantity x squared plus x. And we can't really simplify this further, so that's the answer. That's all you have to do. Part C, we just have to multiply our two functions together, which gives us 1 over x times x divided by the quantity x plus 1. And so the x's cancel out, and we're left with 1 over the quantity x plus 1. For part D, this is the quotient of f and g, which is f of x divided by g of x. So if we look at f of x, it's 1 over x, and we're going to divide that by x divided by x plus 1. So really, when you are dividing something by a fraction, you can write it as multiplying by the reciprocal. So that's what we're going to do. We'll write that as 1 over x times x plus 1 over x. And then we're just going to multiply straight across because they're fractions. And we get x plus 1 in the numerator, and on the bottom we have x times x, which is just x squared. So our final answer is x plus 1 over x squared. The next thing that we're going to cover is called composition of functions, which sounds really scary, but it's really not too bad. So let's kind of break that down. We know what functions are, so really the question is, what is a composition? And compositions can kind of be thought of as arrangements or combinations. If you compose a piece of music, you're writing it, you're putting it together. So in this case, we're composing, we're arranging, we're combining functions in different ways. Mathematicians usually use the notation f of g, and so instead of writing of, because 2 letters is entirely too long to write, they just put a little circle or an O. And so we write this as f o g, and we can put that in parentheses, the quantity f of g of x, which is really just the same thing as saying f of g of x, where g of x is the quantity that is going into our function f. So a composition of functions is kind of like a function within a function. So kind of like a dream within a dream. Anyway, I think some examples always help, so that's what we'll do next. If we're given that f of x is equal to 3x squared plus 2, and g of x is equal to 2x, part A is f of g of 3. So the first thing that I would do when we're writing this example is write f, and then put your parentheses. And what are we putting into f? Well, we're going to put g of 3 in there. So we'll write g of 3, and then we have to close our parentheses for our f. So f of g of 3. So what is g of 3? Well, it's just 2 times 3. So 2 times 3 is 6. So f of g of 3 is really the same thing as f of 6. So all we have to do is plug 6 into our function f, which is 3 times 6 squared plus 2. And if you do the arithmetic, you get 110. So for part B, g of f of 3. First off, let's just put g and then parentheses. So this is our g function, and what are we putting inside of our g function? Well, we're going to be putting f of 3 inside of it. So we have f of 3 inside of g. So the first thing we have to do is we have to evaluate f of 3. So 3 times 3 squared plus 2. And that gives us 27 plus 2, which is 29. So we have g of 29. Well, what's g of x? It's just 2 times whatever we're putting in, which is x. So 2 times 29 is 58. So not too hard, but you have to be aware of what order your functions are, because it does make a difference. They're usually not the same thing, f of g and then g of f. For part C, we have f of g of x. So g of x is going to be put into our function f. So g of x is also the same as 2x, because they're equal. So we can put 2x into f. So we have f of 2x, and we have to treat 2x kind of just like a regular variable. So we're taking this thing and we're putting it into our function f, and all we have to do is just plug it into what the spot that is supposed to fit. So we have f of x equals 3x squared plus 2. So if we just let x equal 2x, we have f of 2x equals 3 times the quantity 2x squared plus 2. And so 2x squared is really the same as 4x squared, because you have to square the 2 and you have to square the x. So 3 times 4 is 12, and we still have that x squared there, so we have 12x squared plus 2, and that's f of g of x. And if we wanted to solve for when x equals 3, we could just plug in 3 to that final equation, and we should get 110, which is what we did in part A. So we just found a specific value for 3, or for x, excuse me. For part D, we have g of f of x. So we're just finding the general equation for g of f of x now. So inside of g, we're putting f of x. F of x is equal to 3x squared plus 2. So we have g of 3x squared plus 2. The g function is just 2 times whatever you're putting in. And in this case, we are putting 3x squared plus 2 inside of our g. Doing that, we get 2 times the quantity 3x squared plus 2. Distributing our 2 to both of our terms, we get 6x squared plus 4. And that's the answer for part D. And if we wanted to put in 3 for x, for g of f of x, we should get 58 as our answer, because it's the general equation of g of f of x. So we are going to do example number 4, and this will be our last example. We'll go through number 5 tomorrow in class, as well as any problems that you might have from the homework, and we'll give you time to work on the homework too, if you haven't looked at it. So example number 4, given the functions f of x equals 1 over the quantity x minus 2 and g of x equal to the square root of x, we need to find f of g of x and the domain of the composition. So what x values will work, what x values won't work. The first thing that I would like to do is to look at f of x and then g of x. We're going to look at those separately. So f of x is 1 over the quantity x minus 2. So what is the domain for that function? What x values can we use for this function? Can we use just anything we want, or will there be a certain value for x that will make our denominator 0? And if you look at that, you can see that if x equals 2, 2 minus 2 is 0, which is not good. So we can have any x value. So x is in the real numbers. It can be any number except 2. So that's how we'll write it. X such that x is any real number, but it's not 2. So that is our domain for f. For g, we have the square root of x. And so can we put anything in for x? So the domain for g is any x such that x is greater than or equal to 0. So those are our two domains. Now we'll see with f of g of x that domain, the domain of that composition, is going to relate somewhat to both of these domains for f and g. So let's find f of g of x. G of x is going to go inside of our function f, and g of x is equal to the square root of x. So we have f of the square root of x. So just plugging that in for our variable, we have 1 over the quantity square root of x minus 2. And if we look at this, let's try to figure out where our x values can be. If we were to graph this, we could see that x first off has to be positive, because you can't take the square root of a negative number. So that's the first thing that we need to say. So x is going to be greater than 0. But can x also equal a value where it's going to make the denominator 0? And what value would that be? Well, it turns out that if you take the square root of 4, the square root of 4 is 2, and 2 minus 2 is 0. So we can't have the value 4, and we can't put that in for x. So even though x is greater than or equal to 0, it's positive, it can't be 4. So we have to say x is greater than or equal to 0, less than 4. And then it's greater than 4 and less than infinity. So it goes on forever and ever. It just can't be 4, and it can't be negative. So that will be the domain of our f of g of x. And if we look, it is partially related to the domains of f and g, because g can't be negative, and then f has that one value that makes the denominator 0. So f of g of x is similar in both of those ways. And with that, I would like to conclude the first online lesson for my class this year, for the college algebra class. I hope that you guys got something from this, and we'll talk about it and see if you have any questions or comments just about how the video worked or anything like that. But we'll also be discussing the homework tomorrow and any problems that you guys might have had. So with that, I hope you guys have a good night, and I will see you tomorrow.